am on page 38 right now. I'm kind of flipping through, but we looked at this projectile motion. We should have done section 1 review. And now I am on page 43. Page 43 starts Newton's laws of motion. This is something we should know, right? We've looked and taken notes on this on our sheets. We have researched it some more and created brochures. So these should be really quick notes, right? Right, Mrs. Lon? You got it.
Got it. Good job, Mrs. Lon.
Womp, womp, womp. Okay, so this is 12/8/22 Newton's laws of motion. Guys, by now you should know and anticipate what I'm going to be writing down, right? It's usually titles, section headings, important information. Did you get nervous when I was saying section? You guys all like... All right. Newton's first law of motion. So Newton's first law. This one you should know by heart by now, right? An object at rest remains at rest, and an object in motion remains in motion unless what? Acted on by an unbalanced force. All right, so your Chromebook should be closed. We're not playing games while we take notes. Did you know that multitasking is not humanly possible?
I know.
All right, an object at rest. Something always gets more attention than the other thing. So we're going to focus on one thing at a time, Evan. An object at rest stays at rest. And an object in motion. Open your eyes. In motion. Stays in motion. Unless acted upon by an unbalanced force. Your voice should be off. I am going to underline this Newton's first law. That way it draws my attention to what it is that I'm defining there. Because otherwise it kind of gets lost, huh? An object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. What does it mean to be unbalanced? Okay. So if we're talking about forces and it's unbalanced, it means one direction is more powerful than the other, right? Oh, sorry, you guys know I have ADD, right? Is that okay? All right. So one side is more powerful than the other, it would be unbalanced. So if I was trying to move the desk, I would have to act upon it in an unbalanced way with more force than would be against it, right? All right, so that is, they kind of give you an idea. Look at this. Did any of you use your book when you were looking at making your brochure as suggested? No? So here's a great example and a great visual. This ball is at rest. There is an unbalanced force being acted upon it to be in motion. It would continue in motion forever, except what is the force being acted upon it when the ball is in the air?
I try to hit a golf ball.
Gravity and air resistance, right? Because it's not in a vacuum. It's not in a scientific vacuum. All right, page 44. You know what I didn't write? I should have probably put chapter 2, section 2, right? 44. That was page 34. And this section goes through 47. Oh, I just kidding. It goes through 51.
Wowzers.
All right, part 2. There's another visual here. An unbalanced force from another car acts on your car, changing its motion. The collision changes your car's motion, but not yours. So your motion continues with the same velocity. So have you ever like had your family hit the brakes and your body is like, no?
Yeah, my dad does that. I'm all over the car.
So your motion would continue in that same velocity. Another unbalanced force from your seat belt changes your motion. So you know how the first time you pull on the seat belt, it locks, and then the next time you're like, I can't go anywhere. Like, there you go. You guys are insane today. All right, so then we have some things about friction and inertia. Inertia
The brain chemical.
is the tendency of all objects to resist change in motion. Inertia.
Isn't inertia also that though a brain thing?
An aneurysm? No. An aneurysm is a bleed in your brain. Inertia is the tendency.
I've heard of inertia. Excited or something. I have a lot of inertia.
Tendency of all objects. This video is made for children. To resist.
Oh.
Can you read it from your book though? It's on page 45, guys. I'm always copying notes straight from your book.
Any change or whatever it is, right?
Any change in motion. It's purple word.
It's purple. I don't think it's purple.
On the top of page 45.
Inertia is the tendency of all objects
To resist.
any change in motion due to inertia. An object will at rest will remain at rest. Oh my God, answer it. Likewise,
Oh, lands. All right.
Bad.
So that is inertia. Did we get that right?
Right.
No. You know, on the you know what I found out? Mr. Schiller doesn't even let them use their notes on the quiz. So maybe to help you remember. I guess so. We're gonna have to start, scaffolding that away. All right, next. Mass is a measure of inertia. An object with a small mass has less inertia than an object with a large mass. So first we need to know inertia is related to mass. We also need to know that mass is a measure of inertia. And what do we mean by that? Well, an object with a small mass has less inertia so it has less resistance to move, right? That makes sense, right? An object with a small mass has less inertia than an object with a large mass. So in other words, its tendency to resist is less if it has less mass, right? This here little swimsuit I could toss. It's not really able to resist me much. But if I went over to Elena and tried to move her, it has more inertia, so it would take more force to stop her, right? Because Lola swims first hour.
This is laid it out. I just throw mine in the bag and help spread it. I just throw it in the shower.
That's stink nasty.
Yeah, we still try. We still on Friday. On the Friday? No, Monday, Friday. Oh, wait, Andy, you do it? I've never. No, I just go on Fridays for fun. Oh my god. I do. Like no. Or distracting.
All right. So inertia, mass is a measure of inertia. Let's look at, so their examples they give, it's harder to push a car than it is to push a bike. So this object with more mass has more inertia because it is resisting motions more than the bike is, right? So there's more inertia here than here. So instead of calling people lightweights, you can tell them you have little inertia.
Lightweight.
So when Andrew goes to wrestle someone, you can be like, "Oh, I'm taking you. You have less inertia than me." Right?
I got more.
All right, second law. Second law. We know the second law, but we're going to remember it better if we write it more often, right? This is page 46. The second law states that the acceleration of an object depends on the mass of the object and the amount of force applied. So Newton's second law the acceleration of an object depends on the mass
Yeah. Side of the paper.
Have any of you guys thought further about your gravity lab
Yeah.
and the 3 objects you're going to be dropping?
Yeah.
So if you bring your 3 objects, or if you just want to use objects from the classroom, we're going to do that tomorrow. No glass.
So when I say this as
That's really weird, but whatever.
I'll use
Okay.
I'll use it.
So this is describing the motion of an object when an unbalanced force is acting on it. And as with Newton's first law, it is easier to consider the parts of this law separately. So, of course, acceleration depends on mass.
That's totally uncalled for. It's not spitting out mounds in her room.
In other words, it's telling us if force applied is the same, acceleration of less mass is greater than the acceleration of more mass or greater mass. So they give an example of an empty cart and a full cart of groceries. If I push at this thing,
400 pounds at the end of the grocery.
so at the beginning you can,
She goes to the counter and says, "I hope you spend $200." And it's like 800. I'm like, "Girl, you need to chill."
at the beginning you can go at like a decent speed without having to push it much, right? But otherwise,
You can chill on vegetables. And she always
is your phone supposed to be off and put away? Thank you. All right. The other part is our acceleration depends on force. I gotta switch pages, so are you guys okay on this? Acceleration depends on force. In other words, acceleration increases, guys, when a larger force is exerted. So the last part in this section talks about our equation here, right? You can rearrange it. So if acceleration is equal to the force applied divided by the mass, and we multiplied both of these sides by the mass to rearrange it, not only do we have, I'm sorry, I am skipping a step. We would say that mass times acceleration is also equal to the force. So our initial equation was acceleration is equal to force divided by the mass. So one of these ways we can figure out one of those things. If we were solving for M, we would do what? Nope. Look at this one. If we're multiplying our mass by acceleration, how would I undo multiplying it by acceleration? So I would divide it. So I would say mass is equal to force divided by acceleration. So all three of these equations can be rearranged from one of them. So F equals MA is one that I always recall and remember. And then I can rearrange it to get the others. Are you guys good?
Three guys eating paper. I don't know what's happening right now.
All right, so then you have gravity. This is how they figured out gravity. Okay, so this section review is yours. I'm going to give you a couple minutes to do those 3 questions on page 47. Because there is one little bit of this section before another short review, because of course we haven't seen number 3, right? So be sure you're reading, guys, enough. 1, 2, and 3 here, and taking some time to complete those.